All right, so here's example 4. With example 4 here, we're again looking for a variable that has a coefficient of 1 or -1. So I do notice a variable that has a coefficient of 1 right there. So that's what we're going to solve for. We're going to solve for the x in the second equation. Pretty easy to solve for. We're just going to add the 8y to the other side. That gives us 8y plus 4. Now that we have x equals, we're going to substitute this back into the other equation. Remember, it's always the other equation for what you use to solve. So we're going to replace every x in that equation with 8y plus 4. So we had 1/4 times x. Now instead of x, we're going to use 8y plus 4. Then it was minus 2y equals 1. Now we can distribute the 1/4. We could clear the fractions if we wanted as well. But since everything's divisible by 4 within that parenthesis, we may as well just distribute. That's going to give us 2y plus 1 minus 2y equals 1. Now 2y minus 2y is 0, so that leaves us with 1 equals 1. Hold on a second. Our variables are gone. What just happened there? Well, let's take a step back. We were trying to figure out at what y value do those two lines cross. That's what we were solving when we got down to one equation, one unknown, is what y value is it when my two lines cross? And we found 1 equals 1, which back with linear equations told us that there was an infinite number of solutions, that it was all real numbers. Now, with a one variable situation, it is all real numbers. Remember, that's not our answer here. What that tells us is every y value works. Our lines are crossing at every possible y value. Now, that doesn't mean all real numbers work. It doesn't mean all ordered pairs work. What it means is I've got the same line twice. So there we go. Same line twice. At every y value, there's a crossing. That's what's going on here, is these are the same line. So the way we write this answer is we write it in set builder notation with the set of all ordered pairs x, y such that, and then you can write either one of the equations. Now, here's the cool thing. So a lot of times it's kind of hard to check your answer in a situation like this. If we know that these are the same two lines, they should look the same. You could get them both into y equals mx plus b form if you wanted as a way to check your answer. Now, we could also, in this particular case, from the original problem, we could multiply both sides of that first equation by 4. And hey, look, it matches up to the original second equation. So of course, if the two equations look identical, then they are the same line. And that's what's going on here. But I want to make sure I show this example to point out algebraically what it's going to look like when we have an infinite number of solutions. So when you get down to one equation, one unknown, and you get something like 1 equals 1, 5 equals 5, 0 equals 0, something like that, that's going to tell you there's an infinite number of solutions. Now, it's really, really important that you had done the work prior to that correctly. That, for instance, if we would have taken our substitution equation and plug it back into itself, you're always going to get a 1 equals 1 or 0 equals 0 situation. So we got to be careful there. We got to make sure that we're plugging our substitution equation back into the other equation. That's really, really, really important. So 1 equals 1 again, remember, or 5 equals 5, 0 equals 0 means there's an infinite number of solutions. Now, if, on the other hand, you ran into a situation like 0 equals 1, 0 equals 5, 10 equals 7, that means there's no solution because that's a false statement. That's when your two lines are parallel. So there's no solution if you end up with a false statement like 0 equals 1, 5 equals 2, something like that.